All right, you guys, number 1 should be E. So we should probably talk about a lot of these. A says the true proportion of students at this university with the correct address on record is within the confidence interval constructed. So the one constructed, we're not sure if the true P is in it or not, right? There's either a 100% chance in it or a 0% chance. We don't know which one. All right. 95% of the students at this university have the correct address on record. No, that's not even talking about a confidence interval. C says the true proportion of students at this university with the correct address on record is within the confidence interval 95% of the time. This one was tricky. I could see why you would pick it. The problem is it's talking about the confidence interval that you made right here. And so again, that's just the one confidence interval. We don't know for sure if the true P is in it. It's either in it 100% or 0. This would have to say something about taking a bunch of confidence intervals. All right, D, the sample proportion of students at this university with the correct address on record is within the confidence interval 95% of the time. The sample P is always in the confidence interval because it's in the middle of it. And the sample proportion of students at this university with the correct address on record is within the confidence interval. So this is true all the time, okay? The sample P is within the confidence interval. Yeah, it's right in the middle, you guys, every time. That's how we get our confidence interval, is from the sample P. All right, 32 is B. Rainy days are not independent, so a lot of times, you know, if you have bad weather, it comes kind of all together. So you can't say that one day it's going to be 20 and the next day it's going to be 90, because there's obviously some dependence from day to day within a given week. All right. 33 is D. So if you think about a Venn diagram, this right here represents the overlap, the probability of A intersect B. All right, if this is 0, that means there's no overlap, which means they are mutually exclusive. So it is D. Okay, number 34 is D. 35 is A. So it's definitely not a simple random sample because we want to take from all 5 countries. So a simple random sample, everyone would be grouped together, and then you have the same, every group of size whatever you choose has the same chance of being chosen. So then is it a stratified sample or a cluster? So stratified, you guys, is grouping them alike. And so if we want to get some from each country, then we're grouping them alike so their opinions are alike. A cluster sample should represent the population, and they should all be close together. So you would have like a bunch from every different country in your cluster, which is not the case. So it is A. Number 36 is C. All right, for 37, you have to remember that a residual is always the actual minus the predicted. So this point right here is the actual. So that's the 6. When they plugged in 5, they got 6, actually. But the predicted comes from this predicted equation right here. We would plug 5 in for x and see what we got. We were predicted to get this. And then you got to do actual minus predicted, and you get D. All right, number 38 is B. We plug in 2, and this is how much we would expect it to go up. This is our initial grade if we study 0 hours. So we would expect it to go up by 20.4 points. Okay, any time you take a larger sample, the distribution is going to be less spread out. So if you think about, we're taking proportions, or whichever one you're doing, proportions is this formula and means this formula. Either way, we're dividing by n, so that's decreasing the spread. Okay, at number 40, we want to do norm CDF from 13,000 to 28,000, a mean of 20,500, and a standard deviation of 3750. That gives me 0.954. So our expected value would be that out of those 400, 95.4% has a mean income in between there, and so that would be D. All right, number 3, you want to do a chi-square goodness of fit test because I want to know, is it in the following distribution? So incoming freshmen are in that distribution, so when they graduate, do they stay in that same distribution? So first of all, we need to know of those 200 graduating, or first we need to know out of 200 freshmen, if they're in the same ratio. So if we add up 5x plus 6x plus 6x plus 8x equals 200, we can find x. And then you want to multiply 5 by x, and you got your A and S, and 6 times S, and you got your engineering, etc., etc. So that's how we get this number here. And then you want to figure out which one is expected counts and which one is observed. So the freshmen coming in is our expected counts. We would expect them to stay the same, but this is what we actually observed happens when they graduate, and we want to know if there is a difference. So our null hypothesis is the graduating students major in A&S, English, B&M, and computers in a ratio of 5 to 6 to 6 to 8. And the alternate is that the ratio differs from that given in the null hypothesis, and I'm going to use a significance level of 5%. Okay, this is called a chi-square test for goodness of fit. We're going to have a random sample. They did take a random sample of 200 graduating students. So 10%, we'll assume there are at least 2,000 students at the university. And remember, for large counts, for goodness of fit, it's greater than or equal to 5. And you have to remember that you will always use the expected counts to check greater than or equal to 5, which they all are. For the do part, we want to find our test statistic, which is chi-squared. This formula is on the AP exam. All right, it's always the observed minus the expected squared divided by the expected plus the next observed minus the expected squared divided by the expected. Okay, all the way down, and we get 22.81. Okay, then we do chi-squared CDF on our calculator, and our lower bound is this. It's always shading to the right on the chi-squared. And degrees of freedom is really important that you know how to find. For goodness of fit, it's just the number of rows minus 1. So 4 minus 1, which is 3. So our p-value is 0.00004. So then we do our conclusion. Because the p-value is less than alpha, we reject the null, which means we have convincing evidence that the distribution of majors among graduating students differs from that of incoming freshmen. All right, number 4. So there are different ways to do this problem. So for A, I said assign the numbers 0 and 1 to the student is able to participate, and assign the numbers 2, 3, 4, 5, 6, 7, 8, 9 to the student is not able to participate. Basically, you just need to make sure that you have 20% that are yeses, they're going to participate, and 80% that are no's. So you could have said just this is a yes, and this is a no, but you would have had to skip the numbers 5 through 9. So I decided not to skip any numbers, but that would also be 20%. All right. So then you want to say where you're starting. So I'm starting at the beginning of the table, read consecutive single digits. We're not skipping any on this one, the way I did it, because it's a percentage. So continue until 3 students who are able to participate are found. So part B, we actually do this. So I have 25211,750, right? Starting there at the top left. And that gives me 3, and I can stop once I get 3 students. So it took me 8 students to ask in order to find 3 who can participate. Then I decided to continue on the same line. You could also say you're going to start on the second line, all right, whatever you decide. And it took me 30 students to find 3 who were able to participate. All right, so this next one is just kind of understanding the graph. So we have our number of students interviewed and how many times it took to find 3 of them. So basically from the chart, we can see 9 simulations that resulted in interviewing more than 20 students before 3 were found. So if I go to this 20 and they asked how often does it take more than 20, we can add up all those numbers. And there are 9 times where it took more than 20 students to get 3 who could participate. So that means the probability of interviewing more than 20 students is 9 out of 100 because they did 100 simulations, which is 9%. So there's a 9% chance that the professor will have to interview more than 20 students before she can recruit 3.